This is actually one of my favorite integrals. It's a very powerful one because we need to prove this statement not just for one n or two n's or three n's. We need to prove it for all n. So you take n, you give me back the integral. Here we'll be using the integration by parts formula. And we will be applying it extensively. I want you to notice that if I choose x to the n to be u, which is the part where we differentiate, and I choose e to the x to be, e to the x dx to be my dv, which is the part which I integrate, then it is a very good choice because in becomes u times v, x to the n times e to the x. Wow, I just got the same term that's inside back again. And then I take away, what do I take away? I take away e to the x times the derivative of x to the n, which is n times x to the n minus 1. Of course, don't forget the dx. Then here's the catch. This is in minus 1, right? So in minus 1 just like we did here, you would get x to the n minus 1 e to the x. So you would get whatever is inside, you would get it back again. You always get it back again. And then you take away the derivative of x to the n minus 1, which is n minus 1, and then the integral of e to the x, x to the n minus 2 dx. So this gives you I to the in minus 2, and so on and so forth. But what's really going on here? Let's see. So this should go on and on and on until you reach I1, which will be equal to x to the 1 times e to the x minus 1, just like n minus 1, n minus 1. And then you get e to the x, x to the 0, and dx. Then this is something we know how to compute. E to the x, the integral is just e to the x. And of course, if you look at I0 is just what I0 is precisely e to the x. And so this would be I0 if you're wondering how it works. But I will just write e to the x because that is nice. And it looks like if we are somehow able to substitute in all the values for I1 all the way to In, then we should be able to reach a solution. So let's see. I'll give myself a little bit more space. And right now I will ignore the fact that this is in minus 1. Or maybe I will not ignore it. But here's what I'll write down. So I'll write down x to the n times e to the x minus n. The integral of this, I know it will give me the exact same thing again. It will always give me the exact same thing. But then if I just literally copy this exact same thing, and I need to be careful with the signs, I get the following. Now this is in minus 2. I'm copying whatever is in here. Notice now that this becomes n e to the x to the n minus 1, and then this becomes positive n times n minus 1 times I to the n minus 2. But I to the n minus 2 is just x to the n minus 2 e to the x minus n minus 2 times I to the n minus 3. And I hope you see where this is going. I'm using the exact same formula that's here, for example. That's what I'm using, if you're wondering how I obtained this. So what I'm trying to say is that I to the n minus 2 is just x to the n minus 2 e to the x dx. We always get whatever is inside of the integral. We always get that. And then we look at the integral of the same thing, but the power is taken away 1 from, and you multiply by the old power. So that is always the common theme. So the old power is multiplied by the new integral, and the old integral stays the same. So that is a common theme. And if we keep doing this, we keep substituting values on and on and on, and then what we will get actually is what do we get? Let's see. Let's do one more. So if I do one more of this, what is I n minus 2? It is the integral of x to the n minus 2 e to the x dx, as we've just said. But that is just going to be x to the n minus 2 e to the x minus the integral of e to the x times the derivative of x to the n minus 2, which will always be n minus 2 e to the x, and then you have x to the n minus 3. dx. So I will write this down now. I get n times n minus 1 of this, and then n times n minus 1 times n minus 2 of that thing over there. But then that is just I3, right? Look at it again before I erase it. This is I3. Okay, so it seems like you can just keep going on like this. And the reality is that I actually can. And if I do this over and over and over again, maybe I do not need this anymore. Here's what I get. So it's this minus that plus this. I mean this whole thing minus that. Now let's agree first that all of these terms will include e to the x. So I'm safe not writing e to the x in every single one of these terms. I hope that's fine. So I do like this. Then we said n times n minus 1 times n minus 2. I3, so we'll probably get, again, so I'm just reminding you, we'll get e to the x, x to the n minus 3. But then e to the x is a common factor. So this looks like a common theme. I have the power, let's say n minus 1. So I multiply by all the numbers from n to n. If I have until n minus 2, so I multiply by all the numbers n and then n minus 1. Or if I have n minus 3, I multiply by n times n minus 1 times n minus 2. So I hope you can see this pattern that's developing. And also, be very wary of the sign change. So, there's a positive sign here, and then a negative sign, and then a positive sign, then a negative one, then a positive one. But I really want to get to the end of this. So here, when we took away 3, we had 3 terms. We took away 2, we had 2 terms. When we took away 1, we had 1 term. So if we want to get to the end of this, we would go to 0. And to go to 0, we need to take away n terms from n. And so if you want to count n terms from n, then you just count until 1. So we're multiplying all the numbers from 1 to n to get x to the n minus n. And so, in that case, the product of all numbers from 1 to n is just n factorial. Next to the n minus n is just 1. Now, if we go one step before that, you get n minus n plus 1. So you should have n minus 1 terms. You should have n times n minus 1, until 2, and then, until 3, and then 2. So that should also be n factorial. So we're considering this by looking at the number of the index that's being taken away. So n minus 1, that's another way of saying 1. And when I say this, I mean inside of the brackets. That's another way of saying x to the 1. And then x to the 2 would be n minus n plus 2, or n minus 2. So you would have n minus 2 terms. So n all the way until 4 and then 3. So that's n minus 2 terms for you. That's another way to write 2. And so on and so forth. So it looks like we found this, what we found is a way to write the coefficients. Now I'm not sure about the signs. So I'm just putting some random signs now. But what I am very confident about is that I can now write the sigma notation. I know that I have n plus 1 terms, because I start with x to the n, and I end with x to the 0. So from 0 to n, there are n plus 1 numbers. So it's k is equal to 0 until n. E to the x is a common factor in every single term of these. And then the sign alternates with every step. The first step is positive, so if k is equal to 0 is positive, k is equal to 1 is negative, k is equal to 2 is positive, and so on and so forth. Okay, and you always get x to the power of something. I would like to have the first term to be x to the n. Then I would choose, the first term is x to the n, second one would be x to the n minus 1, x to the n minus 2, so on and so forth. I think you see it now. We should probably take x to the n minus k, because if we take that, then it makes sense. As we increase the k, we get less powers. But then how do we describe this coefficient? So we've already made the observation that when you take away 1 from the power, you multiply by 1n. When you take away 2 from the power, you multiply by n times n minus 1. When you take away 3 from the power, you multiply by n times n minus 1 times n minus 2. So how do we describe this? This is actually not too difficult. So if we start with n factorial, and then we divide by n minus k factorial, then here's what we get for the first, let's say, 5 values. For k is equal to 0, we have n factorial divided by n factorial, which is 1. For k is equal to 1, we get n factorial divided by n minus 1 factorial. Well, guess what? N factorial is just n times n minus 1 factorial. So they cancel out and you get n. K is equal to 2 is the same thing. N minus 2 factorial. And here you have n times n minus 1 times n minus 2 factorial. This is the same way of writing n factorial. And I get n times n minus 1. So, okay, this seems to be working. When you take away 2 from the power, you get n times n minus 1. And if I take 1 from the power, I get n. And let's say I take k from the power. Oh, no, not k, I take n. So let's say I have n factorial over 0 factorial. This should give me n factorial, right? And it does. We just verified that. We know that this is true because this has the coefficient x to the 0. When I plug in n here, I get x to the 0. Same thing for this one. If I plug in k is equal to 1, then I get n minus 1. And also here I get n factorial divided by 1 factorial. So the coefficients are at least consistent in that regard. So more or less you could say that this is another way of verifying that the coefficients actually work. It's a really good way to look at it. So this is the correct formulation for the problem. Almost, because if I end the video now, I will be guilty with forgetting a very important constant, c, which would cost me a lot. And it would also cost you a lot if you forget it. So do not forget it. And more generally, this is how you solve problems of this sort. You need to look at different values, you need to try different examples, and you need to acquaint yourself with the expression itself. So if it's in n and you don't know what's going on, you might plug in n is equal to 1 or n is equal to 2, and so on and so forth. And then you can get to know what you're dealing with more thoroughly. And then that should be a good step towards finding the final solution.